Good morning, everyone. This is Sachin Fiske from Electrical Engineering Department, Assembly College of Engineering and Research Center. In the previous chapter, we discussed about the stability. Now, what is stability analysis? Let us discuss here. So basically, we are going to start our introduction point related to stability analysis. Most important problem in linear control system concerns stability. That is, under what conditions we will a system become unstable, and if it is unstable, then how should we stabilize the system? Stability may be defined as the ability of the system to restore its equilibrium position when distributed, or a system which has a bounded response or a bounded output. Stability analysis in a complex plane. Basically, the stability of a linear closed loop system can be determined from the location of a closed loop pole in S-plane. If any of these poles lies in the right half of S-plane, that is RHS, either the poles are real or complex as shown in figure, then with increasing time, they give rise to the contaminated mode, and the transient response increases monotonically or oscillates with increasing amplitude. Either of these systems represents an unstable system. For such a system, as soon as the power is turned on, the output may increase with time. If no saturation takes place in the system and no mechanical stop is provided, then system may eventually be damaged and fail, since the response of a real physical system cannot increase identically. See this diagram, pole located in RHS gives unstable response. Consider a simple feedback system as shown in figure. Here, RFS is the Laplace transform of the input, C of S is the Laplace transform of the output, G of S and H of S will be the gain and feedback of the system, and E of S is the error given by the system. So here, overall transfer function is given as per the definition of transfer function, C of S upon R of S is equals to, as both the loops are parallel connected with feedback system. So G of S upon 1 plus G of S into H of S. And this characteristic equation is of the above form is 1 plus G of S H of S is equals to 0, as the denominator is equalized to 0. The root of the characteristic equation is called as the closed loop poles, and the location of such roots or pole on the S-plane is indicated in a condition of the stability as shown in the above figure. The stability condition based location of the closed loop poles is shown by this equation. Here, root stability criteria is given, and since most linear closed loop systems have a closed loop transfer function of the form as C of S upon R of S, where A's and B's are the constant and M is less than or equal to N. In the equation, C of S upon R of S is equals to, in numerator, B0 S to the power N plus B1 S to the power N minus 1 plus so on. And in denominator, A0 S to the power N plus A1 S to the power N minus 1 so on. So we must first factor the polynomial A of S in the order to find the closed loop poles. The characteristic equation of a simple feedback system can be written as a polynomial as A0 into S to the power N plus A1 into S to the power N minus 1 plus A N minus 1 into S plus AN is equals to 0. There are two necessary but insufficient conditions for the root of the characteristic equation to lie in the LHS of the S-plane. Number one, all the conditions, that is AM plus AN minus 1 plus AN minus 2, A1 and A0 should have the same signs. where none of the coefficient vanish. That is, all the coefficient of the polynomial should exist. By this way, we judge the absolute stability of the system. Let us take one example, that is, the given characteristic equation is A of S is equals to a to the power 6 plus 4s to the power 5 plus 3s to the power 4 minus 2s to the power 3 plus s square plus 4s plus 4. If the system described by the characteristic equation is stable, one coefficient is minus 2, that is negative, and therefore the system does not satisfy the necessity condition of the stability.